So we will work like this. I assume that during the weekend you forgot everything. So I will start with a brief reminder. Okay? And then we will continue all week. Okay? And Maxim, please let me know if my board is not clear.
Okay.
So what we have discussed first, and most important, definition of QFT. And all my course is an example for this definition. And this is the most important question in mathematical physics. What is QFT? So I explained that it was functor from geometrically enriched cobordisms to tensor algebra. And this is called symmetric and monoidal. Then there was the main example, main simplest. It was quantum mechanics. And I want to make the following important remark. No H bar in the definition. And this is remark number one. And there is also remark number two. No fields. So how could it be that quantum field theory has no H bar and no fields? It's a good question. And my personal opinion is that it is because of this phenomena, quantum field theory was not well understood during last 70 years. You think that it contains H bar and fields. However, there are no fields. So let me write here something that functor was exponential of TH, D equals to 1K. Point number three. So let me postpone the equation of where H bar is. What about fields? It turns out that fields, what we call fields, are or is, I'll write it like this. Concept of fields is a derived concept, not fundamental. You see, I put here exclamation mark signs because it's very, very important. And here we had a definition of local observable. So local observable is the field. So, quantum field theory is a theory where you have local observable. So what is the field? Field is something associated to the point in the space-time. So if you have local observable associated to the point in the space-time, you may call it field. So this is how BPZ Белавин, Поляков, Замолодчик understood quantum field theory through existence of local observable. Now for D equals 1 case, it was nothing but operator. In L, where function applying to a point gives you L. Now, point number 4. What I said. Point number 4. It's a question how to construct QFT. In the one-dimensional case, you have a universal solution. So you do not need to construct. Take any L, any operator, you have a one-dimensional QFT. The question is how to construct QFT if the dimension of the space-time is greater than 1. And here I told you the following. Local observables, so-called fields, correspond to deformation. So let us start with this. What is written here? Here you have an X. Here is the boundary. Here is a point. And here is local observable at this point. Now, I want to say that the deformation of the function is the integral where P belongs to X. Then you may ask, how do we integrate? Of course, we integrate with some kind of a measure, mu. And measure, of course, depends on geometrical data on X. And it is interesting that if you consider such thing, you have a deformation. When we have such situation, we say the deformation that deformation is internal. It means that having an object, we know how to deform it. The object, in our case, quantum field theory, contains enough of structures to be deformed. Okay? And also there was an example. D equals 1. And this nice formula. This is the deformation. I put epsilon here. And it equals to something non-deformed plus epsilon integral from 0 to t e to the t minus t tilde h o e to the t tilde h. And this exactly corresponds to O at P, such that this distance is T tilde and this distance is T minus T tilde. So this works. Okay. So do you have any questions to what I wrote on the board? I really want questions. Don't think that you would interfere the talk by your question. By asking questions, you are helping me to give this rather difficult talk.
What corresponds to the boundary of x in on the left hand side?
On the left hand side, functor to the boundary of x is some vector space L.
I mean, on the right hand side, what is?
This thing belongs to L star tensor L. So this point corresponds to L star. This point corresponds to L. The full thing corresponds to element of L star tensor L. Now we expand in epsilon. L is the same here. What happens here? So you see it's a formula. But this formula corresponds exactly to the point P placed on an interval, on a distance T tilde from the beginning. You may ask why I wrote this formula. So what should correspond to this? By functoriality, I can cut it here and here. And by functoriality, it is this interval with a distance t minus t tilde. Here I have a point. And here I have another interval with the length t tilde. So this interval corresponds to e to the t tilde h hat. This small interval corresponds to the operator, to local observable O. And then last exponent corresponds to the second interval. And due to functoriality, I am taking the product. And now I need to integrate. And of course, I integrate with the measure dt tilde. So geometrical data is kind of a metric here. It's geometrical data. So it is very important for you to understand the meaning of this formula. Because in the simplest example, we have classification of all quantum field theory. And this general statement does not depend on dimension. So that's why it is very important to see what happens in dimension 1. Maxim?
Yes, I want to ask a question. I believe that measure in integration at left side of desk was in the factor F.
Was what?
Excuse me, could I speak in Russian? Мне казалось, что в прошлый раз вот эта вот мера интегрирования в дельте F, она была зашита где-то в самом F. У нас было F такое, что оно лежит в там функциях, крест, два пространства, крест дифференциальной формы.
Okay, so actually, so it is a subtle point that I kind of omitted from the very beginning. Yes, of course, this thing depends on geometrical data. But when we deform, we may use some extra geometrical data. Let me give an example. Let us come to this example as a typical one. Suppose that h is 0. So the value of the functor on an interval is 1. So it does not depend on the metric. However, when I'm doing deformation, I need to construct some measure.
Okay.
And I'm using metric like this to construct this deformation. So when we will come to examples, we will see more of it. Okay, Maxim, how can you see my board?
All right. There is no blurring.
No blurring, no disfocus. Okay. It's because now I want to erase it. Actually, this is very hard to understand. It is simple in examples, but you would not find it in the textbook. There are a few people in the world who understand it. And among them, Kansevich, Siegel, Gregory Moore, probably Nekrasov. I don't even think that Witten treats it this way.
Полю Решетихина забыли.
Yes, Reshetikhin, of course. And some of my students. And also Telemann. So people, so you see there are hundreds of people who are trying to do quantum field theory. They wrote like 50 or 100 books. But most of them are outdated. People are typically copying old books and saying something that does not exist, like functional integral. I will come to functional integral a bit later.
Professor, excuse me. Can you hear me?
Yes, sure.
Oh, okay. I have a question. In the integral is the O or theta, theta p or OP. It's a constant or it depends on the parameter t.
It's a constant.
It's a constant. Okay.
If you just have a look here, you may see that it is just very small interval. So there is parameter t here, parameter t here. Why I call this p in the middle of the interval? Because some time had passed from the beginning to insertion. And then some time had passed from this insertion to the end. So when I write it like this, I say that point P has some coordinate, P tilde. But when I'm writing what corresponds to this picture, I'm using functoriality to cut. And I see that this small interval knows nothing about T tilde and T minus T tilde.
Okay.
I'm sorry, I need to take my cat out of, okay. So cat, if you are here, yes. I see the blick. I try to find, I think it's the sun. 1 second, I will kill the blick.
So if we choose the p to be the O in the interval to be identity, then nothing will deform, right?
Yes. So
Okay.
let us make, you see, suppose O is identity. Then I write it like this. So it is a deformation. It actually is a deformation. Because in this case, e to the th would go to e to the th times e to the t epsilon. So it is a deformation. So putting in identity and integrating is a deformation.
Okay.
So later on, when we will come to more examples in quantum mechanics, we will say that this is the zero energy deformation. You are shifting Hamiltonian by epsilon.
Yes, and actually, I understand it by I get firstly I guess theta this one in the integral is depending on time on the parameter t. Can it not be a constant? Because I have
It
an
is not
image
constant.
that it is an image.
Depends on t.
In the integral, actually you say it is a constant as theta or O.
Yes, so it could be a constant. If it is a constant, okay. If it is a constant, let me consider this special case. If it is a constant, then this term, so I will get e to the th
Yeah.
plus epsilon times t
Yeah.
times e to the th. So if I have a constant here, this term cancels. but I'm left with e to the minus t, to the ETH. And I integrate 1, I'll get t. So it's exactly the first term in expansion of t, h plus epsilon. So I like your attitude. So whenever there is a formula, it is good to test it for the simplest possible case. Okay?
Okay. And here it is 1. And in the general case, we can take the function to be any function depending on the parameter t to the range of matrix the linear transform, right?
So
Inside
general, any operator.
any
In general,
operator.
Any operator.
Yeah, from the time parameter t to any linear transformation, right?
So what stands here? So let me write it. This O belongs to endomorphism of the space.
Yes, but I guess it depends on t. Yes. Is it also depending on t, on the parameter t?
In this, no, it does not depend on parameter t.
Okay.
I say OP, it's a symbol that O is placed at point.
Yes, but this point is depending on t.
Yes,
on t tilde. Yeah, t tilde. Yeah.
Point
I'm wrong.
on,
It's t tilde,
but
right?
operator is not. So, because this operator is something that corresponds to infinitesimally small interval around point P.
Yes.
Okay, so may I ask?
Sorry, Professor, I have another question. In this integral, it seems that we make a conjugate to the theta to something like a point. But is it possible to write this integral into a finite sum? It just seems like the integral is something like infinite sum. So is there any definition?
Okay, let me try to comment on finite sum idea. You may ask, how did we guess that it should be an integral? Okay?
Oh, yes.
Because when we started with this factoriality, there was no concept of an integral there, right? And it is a very important issue. That's why I would like to comment on it. You'll see later why this is very, very important. Suppose we have f associated to the interval, okay? And let us decompose this interval, say, in four smaller intervals. It's an example. Now, I'd like to understand the formation of it. So deformation of F is deformation of these four guys. And then I am applying a Leibniz rule to the product. So it is delta F, and I write it like this. And here I have F, 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 plus F, delta F, 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 plus F, F, delta F, F. So these intervals I call 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then the last term. Now, I can use functoriality to simplify this. And this is delta F. Here I have interval 1. And here I have F on a longer something. 2 plus 3 plus 4. Now, what stands here? I have F at 1. Now I have delta F at 2. And now I have F 3 plus 4. And here I have F on 1 plus 2. Delta F at 3. And here I have F at 4. And then I'm going to the very last piece, F of 1 plus 2 plus 3. Delta F at 4. Okay. So in all this exercise, I say that delta F on 1 plus 2 plus 3 plus 4. The delta F on the long interval could be expressed in terms of F on long, relatively long intervals. And here I have delta F on smaller intervals. Okay? Maxim, do you get it?
Yes.
And then I can say, instead of having 4 small intervals, I want to take 400 or 1 million. And that's why if I have 1 million small intervals, I will have 1 million terms. And this would be the approximation of the integral. And when I divide into 1 billion pieces, I am getting the integral.
Excuse me,
Yes?
could you repeat, please, your sentence now? Я просто не вполне понял, на какой именно вопрос вы ответили. Вот, я поэтому чуть-чуть...
You see, I'm trying to answer the following question. How one can anticipate that the result would be an integral?
Okay.
It looks as a miracle. When I was writing functoriality condition, there was no integral. It was something that f on something was equal to f times f. No integral. So the question was, where did the integral came out? And just to explain it to you, I was considering the simplest example. Let me decompose the long interval into 4 smaller intervals. And I see that there is a deformation on the smaller interval surrounded by something that is evolution along long interval. So if I would decompose it not into 4 pieces, but into 1 million pieces, this finite sum would become an integral. So
Yes,
so deformation on the big interval is given in terms of deformation on the small interval. And this question is so important that I went into some detail.
It seems that we just want to maintain the derivative property to the delta operator.
Yes, but it is kind of obvious.
Yeah, yes.
So
Yes.
what is written here? I have a map from an interval to something, and then I'm changing this map. You see, this map is not something very not understandable. It's something very simple. You take an interval, you associate a linear operator to it. Now, if you change the function, of course you will get this. Since this is this, then you change f. You change f here, 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 and here. It's not very fancy.
So we need a limitation process to prove the existence of delta f over a point, right?
Yes.
To define the integral.
So then the question that I need is the continuity or even differentiability of the map f of I. F of t. However, I know that f of t is just exponent. So you see, here I am not giving proofs. Here I am translating to you the feeling of what functorial quantum field theory is.
Yes. Is this limitation related to the observable or pre-observable this concept you defined before?
So,
Mm.
so in this case, so in this particular case, I just want to say that I have f of delta t is small, and then I change it. So f was a linear operator. So this delta f of delta t is nothing but some linear operator. I can take any linear operator here. And I know the answer. I know that the answer would be this. And here I put epsilon, where O is nothing but delta F. O is the limit where delta T goes to 0 of delta F, delta T. So I assume that such limit exists. Let me assume that such limit exists. Then things go well. But I know the answer, you see? Formally, I can say that I know that I have classification of all one-dimensional quantum field theory. I already have the classification. I'm just illustrating, using this classification, this principle. And principle is that in order to deform a theory, you just integrate local observable. You see, now I want to come to a very subtle point. And that's why I will do it only after the break. Okay? Now let us have a 10 minutes break. So we would start at 10:02 Moscow time. That is 3:02 Beijing time. Okay? And we may continue discussion after the break. Once again, my goal is not to provide you with a lot of information. My goal is to teach you how to look at quantum field theory from my perspective. Okay? So my goal is in teaching. So that's why I appreciate questions. I'm very grateful to everybody who asked questions. So some people say that Chinese students do not ask questions. It's wrong. Chinese students do ask questions. Okay. So we will continue in. Let me try to continue. But before I'll continue, I want to make the following remark. I am teaching in Zoom for 3 years, and 1990 years ago, there was another professor who was teaching for 3 years. And he had 12 students. At the moment, I have 13. And when other people ask him why there are so why there are not so many students, he said that a lot were invited, but only few selected. So, Maxim, do you know who was the name of this person?
Я боюсь предполагать, но мне кажется, это Пифагор. Ну, нет, сейчас 1900 лет назад сказать. Нет, я, в общем, не знаю. I don't know.
Okay, Jesus Christ.
Окей.
Okay, so I hope you see my teaching would not be that disastrous as his teaching. Okay? But what I'm teaching you is also quite radical. It's almost radically different from what you can read in books. Now, let me come to the most interesting question. And this most interesting question is, why I'm saying that the only explicit example that we have is in dimension 1. What is so bad in dimension 2, for example, that I cannot solve functoriality axioms just like I solved it in one-dimensional case? And let me tell you the truth. The truth is that if I have a cylinder and if I cut it, okay, I will get something that is a small cylinder. But if I have this small cylinder, I could not create this thing. Now you may ask, why do I need this thing? I need this thing. Let me write it. I need this thing to create field. So what is the field? I need to have small hole. Well, that's why I need this. And having only cylinders, I cannot do it. The way out is to allow to cut X by surfaces cutting boundaries. So I actually would like to do the following. I would like to cut this, not only like this, but also like this. And here I am cutting boundaries. So if you allow me to cut boundaries, I will do the following. I will cut, say, my cylinder into rectangles. And if I have a rectangle, I can cut it again to get triangle. And having triangle, I can get any surface. You see, today is my day of exclamation marks.
Yes. Мы можем уже только триангулируемый так получить. Ну, в смысле, то, что прям любую поверхность, это как-то сильно, нет?
Any surface, any surface. Maxim, you should try to speak English.
Excuse me, okay.
See, please. So you may use the Russian only if you cannot express yourself in any other way.
Okay, excuse me, yes.
Because science, the language of science is English. So Russian is the local language, regional language. So, main problem is to find higher categories. That includes cobordisms with boundaries. Cobordisms, here I say geometrically enriched. So here we are coming to mathematicians, and mathematicians would say that we always have something that we need. It's called higher category. Where you have objects where you have morphisms. So these are called horizontal, and these are called vertical. And here we have this thing. It's called two morphisms. Or morphism between morphisms. So in order to properly formulate quantum field theory in a constructive way, we have to go to mathematicians for higher categories. Not because we like mathematics so much. So I like it, but it's my personal taste. I want to tell you that we have to do it, because it is a very natural language. We need this language to describe quantum field theory. in a constructive way. So this thing should be two exponents, whatever it may be. So higher categories, higher exponents is what we actually need to formulate and study quantum field theory. And this is something that you will not read in books. Now, let me illustrate in a hand-waving way. How can I understand the deformation concept? Now my main object would be something like a rectangle. Now I'm cutting rectangle into small rectangles. And this thing, and here I expect that there is a function. And this would be two morphisms. Okay? And then, if you would like to understand what this thing means, it should be f of this, f of this, f of this, f of this, and here I will say hs of it. So you may ask, what is hs? hc. hc is a higher composition. So when you have ordinary composition, you have a morphism, you have another morphism, 1, 2, 2, 3. So here we have composition of these two. And this is something like 1, 3. And we understand it in category theory. Now, here we have to do higher category theory. And here is the higher composition. It's an operation. In this case, higher composition is an operation on the table. It corresponds to gluing small rectangles into big rectangles. And elementary things is composition of this into this, and also composition of this and this into this. You see, I'm drawing you pictures instead of giving you dull definitions from higher category theory. I want you to have a feeling, to share my feeling, that this is the only way to formulate non-perturbative quantum field theory. Now, how deformation goes? I applied delta F here. So delta F applied to the table is the sum over ij. And here I have the same table with delta F standing here and F sitting at all other places. I, J. And then what we have in the limit? 1 million small rectangles. And we integrate this point P over X. And here we have this hole. And what we put to this hole would be a local observable. In the center. So I address to your imagination. Maxim, could you help me?
Yes.
Could you imagine what happened?
It was easily for me if you write definition, write mathematical definition of higher morphisms, because I lost. I can't understand you at moment where you try to paint squares. В общем, excuse me, I speak in Russia. Я потерял ниточку на моменте, когда вы нарисовали композицию вертикальную и композицию горизонтальную. Я пытался понять, что это такое на, значит, языке, ну, вот, два морфизма. Ну, то есть картинки понятны, но я строго вот определение хотел понять.
Okay. So I need to explain what is the vertical composition and what is horizontal composition. So you may go to any book in higher category theory, but in my real life, I spent 3 years on the Department of Radio Technics and Cybernetics, Radio Engineering and Cybernetics at Moscow Physical and Technical Institute. And we had no categories there. But what we had there, we had chips, okay? Okay. Higher categories for engineer. Okay. So two morphisms. Sorry, two morphisms is a chip. Very simple chip. It is something that has black input, black output, white input, and white output. Okay? Not a transistor, but a chip. And what can you do with these chips?
Connect with another chips.
Yes, you can connect black output with black input.
Okay.
So you may call it horizontal composition.
Ага.
But what else could you do? You can connect it this way. Horizontal composition. And here is the vertical composition. And now, what is the associativity? Associativity means that the result is independent on the order in which you are connecting chips.
Okay.
So suppose you have 3 chips. You can either first do this to get I'll draw all lines. You are connecting this first. So it's the first operation. And then you connect it this way. Okay? So first you make gluing here, and then you do gluing here. And this is the product, okay? So Chinese people know about electronic manufacturing. So let me call it 1, 2, 3. 1, 2, 3. 1, 2, 3. So associativity means that you have production line 1. First, glue 2 and 3, and then glue 1, 2, 2 and 3. Production line 2. First, you glue 1 and 2, and then you glue 1 and 2 with 3. Associativity.
I can understand what is associated in horizontal or in vertical, but why in excuse me, что такое ассоциативность, если я пытаюсь их склеивать не только вертикально и горизонтально, а как-то, ну, вот.
Okay, associativity means that. So, to associativity means that big chip is the same independent on process of gluing. So you may start with this, glue this, then glue this, then glue this.
Ага.
The result would be always the same.
Окей, I understand.
And this is higher associativity. And if you have a structure that has this higher associativity, you call it higher category. So category is when you are doing only resistance, when you are gluing this. It is associativity. So when we have associative algebra, we are saying about it in terms of words. A, B, C, D, we say A, B, C, D, where A, B, C, D are operators with associative multiplication. It doesn't matter how we put brackets. We work in words.
Yes, okay.
And here we are working with, I would say, table of letters.
Okay, I understand you. Thank you.
So this is much better than to write down this dull definition. So once I was at IHES, Institute of High Etudes Scientifiques in Paris. So it was an institute that was created to hire 3 professors in mathematics and 3 professors in physics to talk to Grothendieck. I hope you know who Grothendieck was. So Grothendieck died, but institute was still there. And they are still keeping 3 professors in mathematics and 3 professors in physics. And to be a professor in mathematics, you need to be at the level of field laureate, how to say it, Fields medalist.
Middle. Yes.
And one of the professors there was Kontsevich. And once I was attending his talk. And during his talk, he was drawing pictures. At the same time, there was his scientific advisor. So Kontsevich was very great at that moment, but his scientific advisor was still alive. His name was Professor Goncharov. And Professor Goncharov, being scientific advisor, was quite skeptical during the talk. And he said, Maxim, why are you drawing pictures? Why cannot you, as a normal mathematician, write in line definition of what you are talking about? And then do you know what Maxim Kontsevich said? He said that the subject I'm talking about is proper, could be properly described in the 2-dimensional world of pictures, rather than in 1-dimensional world of sentences. So here I'm quoting Maxim Kontsevich. These pictures give you better understanding of what's going on. If you need, you can put it in words. It's an exercise.
Okay.
It's dull and not illuminating. So just imagine how you are joining these small chips into the big chips.
Okay, thank you.
And this would give you the definition. and also see that this big chip is nothing as a space-time. So that's how we should think of quantum field theory, like the result of a big chip. And then it is clear what to associate to such a chip, to a small chip. Let me associate vector space L here and vector space V here. So this small chip is, so it belongs to L star tensor L, tensor V star, tensor V. So you may call it B operator, okay? And if you later on would like to see triangle, so what is triangle? So put space W here, here, and here. So triangle is, so it belongs to W times W times W. So it is better to consider these lines being non-oriented. I assume that W is isomorphic to W star. And I have a name for it. Nobody in Russia likes this name, but I like it. How would you call this object that corresponds to triangle? Maxim?
I haven't idea.
But I have it. It's called triperator.
Ah. Okay.
So it's my name. It's not a standard name. For me, it's triperator.
I try to understand why in Russia, why Russians don't like this word.
Because of tripper, of course.
Ah.
So it is a triperator. I cannot find better word. So if you would like to understand two-dimensional field theory, you need to go to the world of triperator. And right now, we are writing a paper with two collaborators, with Pavel Mnev and Justin Beck, on how to get topological quantum field theory of triperator. But we cannot call it this way. Okay?
There was some question in chat.
Thank you. Thank you. You see, I need to get a bigger screen to see the chat. Okay, upper half plane case. You see, to get an upper half plane, and here I have this single infinity. This is an upper half plane. These are inputs. And the rest goes to infinity. The rest is in nirvana. Infinity is infinitely far away. So it's somewhere there. Okay, and theory of triperators. Now geometrical data. If you have rectangles, they have two sizes, T1 and T2. And it is clear that if you join it, okay, I'll call it X and Y. X1, sorry, X is horizontal. Y1, Y1, X2. So when you are gluing rectangles, the result is Y1, and here we have X1 plus X2. And if you are gluing them vertically, you get this. So that's why with rectangles, it is easy. However, it's not that easy to have a hole in rectangle theory. So what is the local observable? What could be? One, two, three, four, five, 6, 7, 8. And here we have a hole. It's an annulus. And then you can make this hole smaller. And when you are having this hole smaller, you are getting a local observable. So this is the local observable. So local observable here is a B operator. Associated to square, to rectangle. Is a B operator. So this is how Dirac-Segal axioms or factorial axioms should be modified. So I am telling it to you because I think you see that this modification is very natural, at least from a radio engineering point of view. You are making big chips out of small chips. So what is the variation of this table? Okay. It is sum over ij. Again, the table. Okay, variation of functor types. You have here variation of f I j, and you have f on the rest. Maxim, let me treat you as a what we call control listener. Do you understand?
Could you repeat last word, please?
I would like to treat you as a control student.
Control.
Student.
Yes, yes, of course, yes, I understand you.
So in Russian educational system, professors sometimes have control students.
Контрольный слушатель, yes, I understand. Okay.
And if control student understands, it means that the rest also understand. So control to be a control student is a hard job. But it turns out that control student understands it better than other students, because he is the main target of the professor. So do you understand this picture now?
Yes, a generalization of your calculation sometimes ago about linear case.
Okay. So that's what's going on. So today we had a hard day, right? And my rule is no more than 45 minutes. I have spoken for 43 minutes. So I'm waiting for questions.
Professor, excuse me,
Yeah.
I have a question. In the rectangular grid case, do you assign some algebra structure to each rectangle? And I want to confirm, is the structure just in the parentheses of V star tensor V star, V star tensor V tensor L star tensor L?
So it is exactly
It's the
so I associate to rectangle this thing times, let me call it directly, function on R plus square. What is R plus square? Size of the rectangle. You see, just imagine that I am, like in my youth, a simple-minded radio engineer. Okay.
yeah. It's similar to the one-dimensional case that the adjacent interval can have a multiplication in the sense of matrix multiplication. And
exactly. That's what I mean. Is that matrix multiplication has a natural two-dimensional generalization, and in this way, quantum mechanics has a generalization called quantum field theory.
I see.
So it was my message. My message is that there is no boundary between one-dimensional and two-dimensional story. So when you go to standard course in quantum mechanics and quantum field theory, people will tell you people would say quantum mechanics is one thing. Probably they will write e to the th. Okay. Then when you go to quantum field theory, they will write you something different. And then they'll tell you very indirect connection between one and another. So the logic of my course is that they are not that different. That rectangle is a natural generalization of an interval.
Yes.
And the only problem of people who were not doing it before is just lack of imagination and the lack of good taste. And as Nikolai Reshetikhin is teaching, all this naturally comes from the lattice models in solid state theory, where we have electrons and vertices, and you are writing some Hamiltonians of interactions of electrons, etc. Now you need to try to understand that the space-time is similar to the lattice. And then people start shouting. Lattice breaks rotational invariance. And here I would like to say that in general, all metrics, except the flat metric, break rotational invariance. However, it could be that for some very special metric like this, rotational invariance would be restored. So if you are doing very huge plane, then you will have something like rotational invariance. I think I have a question in the chat. Ah, very good, Bitcoiner. Of course I can define operators like a Wilson line. For this, I just need to draw bigger picture. And since I'm sponsored by BIMSA, I have enough money to pay for my marker. So let me cut out this. Here you have a Wilson line operator, like this.
How do you get the integral for the Wilson line operator?
I have a sum of these things. Just imagine that typically this thing has inputs like this, and it is one in all directions. Okay? Like here we have this id times id. So it's not interesting. However, in some case, this operator is one in one direction, but not one in another direction. Okay? So I call it a gauge field. And then I multiply. So locally, it is like this. So here I have this white line. And you just multiply. And this is pretty close to monodromy. Moreover, if you are that smart, let me tell you that in this case, I do not see the difference between the Wilson line and the 't Hooft line. They are both lines. You distinguish Wilson line from the 't Hooft line if you know which field is electric and which field is magnetic. But in the theories with duality, you do not know it. Okay? There is no way for you to say that this is electric or that this is magnetic. So there are actually only line operators. Okay?
Thanks.
And by the way, if you consider higher dimensional theories, you can have surfaces. And you may call these surfaces strings. Okay? So, any other question?
I lost some. I lost internet connection when you were explaining the upper half plane. I didn't know what was happening.
Okay. Maxim, was there an internet connection? Was there lost on my side or?
No,
It was my problem.
Андрей Семенович, извините, я на секундочку. Мне надо бежать на следующую лекцию. Я хотел попрощаться.
Все, спасибо, Максим. Спасибо. Okay, so how can we understand upper half plane? We may say that there is a distinguished input. Let me call it V for vacuum. Then what could be an upper half plane? Something like this. And here you have V. Vacuum something. In this way, you can draw upper half plane.
So you mean it's it's in one direction? No.
In vertical direction.
Oh.
So upper half plane means that you have a boundary here, but this goes to sky. So I put infinite tower of these guys. So the number of these guys go to infinity. But something is at infinity. And I call it V for vacuum. Okay. Vac. You may call it boundary conditions at infinity. So before you ask me about the upper half plane, you need to ask me about the ray. What is the ray? It is simpler. The ray is made out of this. And here we have an edge of the ray. And the ray is infinite. So how do we understand the ray? We have n of these, and we put here special thing called Vn. And we consider limit n going to infinity such that this sequence, such that the limit of this sequence exists. And this is how we understand the ray. So actually, I told you everything. To understand things like rays, upper half planes, Wilson line, line observables, you just need to invoke some of your imagination. So mathematics is about imagination. Mathematical physics is also about imagination. Interestingly enough, theoretical physics is also about imagination. So when we are using Cauchy language in calculus, we are imagining these infinite sequences and also and also equivalence classes of these sequences. We imagine it. We are not doing that for each epsilon there is an m such that such and such. No. If you can imagine sequences, you understand calculus. If you can only follow axioms of Cauchy, you are not understanding calculus. So Bitcoin, do you understand me?
Yes.
So all these axioms of Cauchy are to give you correct description of something. But then you just understand it. And then you can give definitions by yourself. You see, it's like when you are going to your friend's house for the first time. He gives you instructions. You go here, you turn left, you turn right, you know, this list of instructions. And still it takes time for you to reach his house. But when you will do it like 5 times, you would not need these instructions anymore. You just understand where your friend lives. And you can go there this way, that way, okay? The same with calculus, the same here. Instead of giving precise definitions, I am providing you with a set of examples. So from these examples, you should be able to imagine what is going on. So it is a little bit like Buddha training, you know, Buddha, another teacher, another professor. Bitcoin, do you know who Buddha was?
Yes, I know.
Good. So he also liked when students were asking questions. But Buddha never gave precise definitions. He created images in discussion. And after some discussion with student reaches Satori, enlightenment, saying, now I understand. So that's what I want you to do. I want you to understand quantum field theory. Any other question?
Sir, I have one more question.
By the way, is it possible for me to see your face?
Okay, sorry. Because I'm in the office, I'm a little bit shy. Okay. Hi. Okay. One more question. I think it's a generalization of matrix multiplication, and as we can multiply adjacent operator and sum or integral these you said two morphisms. Can we describe it as an algebra or group algebra?
Of course not, because group is like category. We have only one multiplication as a group. And here we need to understand the concept of two multiplication, where you have two inputs to two outputs.
Okay.
So
as you said,
so how do we multiply it? Like this. So you may understand it in tensor algebra. like you have element V times V star times L star, sorry, V star V, L star L. And then we have another element, V star V, L star L. And then you take a tensor product of them. So tensor product, it's before gluing. And in the gluing, you say take a pairing between this and this.
Yes.
So if you consider this basic element, let me call it E from the word element. You take E1, you take E2, and then you have this partial pairing. So it is this operation. So in linear algebra, we know what does it mean. It is this.
Mm.
Just
Yes.
in D equals to 1 case, E1 belongs to V star times E2 belongs to V star times V. E1 tensor E2 belongs to V star times V times V star times V. Now, E1 times E2 partial contraction belongs to V star times V. So E1 times E2 partial contraction is exactly the same as E1 times E2.
Yes. I understand this tensor model.
Sorry?
Yes. Okay. Can you hear me?
Yes.
Okay. I understand this tensor model by pairing the V star and another V. But I have a more abstract, in some sense, a more abstract model that the two adjacent rectangle represent two groups, and what we are doing, multiplying them is just like amalgamate the two groups by identifying the same element, the same boundary element, I think. Just an intuition, not so formal.
Let me put it this way. In mathematics, two categories are not very often used.
Mhm.
So, you see, we often use groups because we meet groups everywhere in our life. So, when we talk about two group, you may try to think about something as a two group. Say that there is an element E, and there is an operation of vertical multiplication, operation of horizontal multiplication. But please note that when you join them this way, the number of vertical, the number of horizontal things grows. Okay? So the product of two group would be element is not a group element. It has more input.
See.
So what you can do? You might say that you have a universal element, E, that belongs to tensor algebra. Okay. That belongs to the sum over n, L star n times sum over n, L, n. but then it also belongs to times V times V star. And then you may consider E belonging here. So it would be a group element that is taking values in tensor algebra. So actually it would not be a group. It would be an algebra over tensor algebra. Okay?
Okay.
Just look at the picture. As my
By the way, can I understand that this picture as some group action over these left-right arrows, up to down arrows, just like some matrix multiplication over some vectors?
It is a matrix multiplication with one indices. Okay. My engine, you see, friends of me, my roommate that were engineers never understood tensor algebra. So, but they understood tensors. Suppose you have T, I, J, A, B. And suppose we have another T, I prime, J prime, B prime, A prime. Let me define an operation. Let me call it vertical composition. That is V, K, B, I, A, E, K, A prime, J, B prime, J prime. Okay? And they sum over K. I have this, I take these two complicated tensors and I sum up over one of the indices. You may call it partial trace, if you wish. I'm trying to speak the same language as you speak. It is a partial trace. So what the trace is? Trace is if you have operation and you somehow making a loop, okay? It is called partial trace. So I call it partial trace because if you have not an operation but just an operator, you have only one trace. Okay? So this composition may be understood in the following way. You take this, and then you consider partial trace. Like this line goes to this line. Okay, it was horizontal multiplication. But this is actually a partial trace. I think it's the best that I can do here. So linear algebra is great. Linear algebra represents every structure we have in the world. It represents higher category. But to study it, you need to study two operators. So two operators are operations with two different inputs and two different outputs. And then you will get it. Or you can study three operators for triangles. Unfortunately, in the standard courses of linear algebra, people are not studying them. And it's a pity.
Okay, thank you, sir. But back to my question. Yes, can I understand it by some operation over vectors, over multivectors from some input states to some output states. Just like in dimension 1, we would give a vector and multiply by a matrix, then we get a final state.
Yes, you may do it, but the main thing is that it is a partial operation, in the sense that you are not taking all inputs into all outputs. You are connecting, you see here. So we used to do this, and you connect. It is an operation.
Yeah.
But if you have extra lines, when you are taking this thing, you are getting a new chip. I'm sorry. You can go to your radio engineer friends that are doing electronics, and they will tell you, if you take one chip, if you take another chip, and if you join them together, okay, you will not get the same chip. It's impossible. The only thing that you can say, that if you have any chip and any other chip, that sometimes you can make a new chip by gluing something with something. So you should imagine it as collection of all chips. By the way, this connection of all chips has a name in mathematics. And its name is called prop. So prop is something where you have some number of inputs and some number of outputs. And they are numbered. They could be of different type.
Okay, thank you.
So you may consider the following. If you have this prop, you may consider prop also as a prop valued operator. Suppose you have this prop. Then you say you have preferred input and preferred output. Then it is an operator. But this operator takes values in props. So you can understand it as a matrix where each ingredient here is a prop. So we can talk about chips. We can talk about props. The only thing, we can also talk about tensor algebras, but we should not think about it as a group.
Okay, I see.
And at the same time, it is quantum field theory. So the topic of my course was quantum field theory with and without Planck constant. At the moment, I'm talking about quantum field theory without Planck constant. That's it.